Hi everyone, welcome to my algebra seminar. First, this is the first time I took the seminar, and we will study rings and some related algebraic systems. Okay, let us study some definitions first. And we set S be a set, and plus multiply be the binary operation. On S. Okay, the binary operation means A plus B is an element in S, and A multiply B is an element in S for every element AB in S. Then we call the system S and plus be the semigroup. If the multiplication satisfies associative law. Sorry. And the associative law means the sum of AB plus C equal to A plus the sum of B and C. And we call the system be the monoid. Oh, sorry. I was so nervous. Forgive me. If for the first, the system is a semigroup, and the identity in S. And let us see the identity. Identity means for every element in S. Suppose here the identity is 0. That is, for every element, A plus 0 equal to A, and 0 plus A also equal to A for every element in S. Okay, this is the definition of identity. And if we call S the system, be a group if this is a monoid and every long 0 has inverse. Okay, the inverse means for every non-zero element, there exists some minus A in S, or normally there exists B in S such that A plus B is the identity. Identity here, identity is 0, and B plus C also is the identity. This is the inverse definitions. And we call the system, is the Abelian group. If the system is a group and satisfy commutative law. Okay, the commutative law is like A plus B is equal to B plus A for every element A, B in S. This is the commutative law. Okay, and we call the system S plus multiply be a ring. If here's three conditions must satisfied. First, S plus is a Abelian group. Second, S multiply is a semi-group. And the second, S satisfy the distributive law. Sorry, here we use the blue color. Actually, the distributive law also we divide into right distributive and left distributive. And the distributive law means A multiply B plus C equal to A multiply B plus A multiply C, and A plus B then multiply C equal to A multiply C plus B multiply C. This two is left and right distributive law. Okay, and we call the system S is commutative ring. If S is a ring, here we simplify the system S by S, S plus multiply by S, and here we simplify it. This is S. S is a ring and multiplication satisfy commutative law. Okay, and we call S be a division ring. If S is a ring and 0 not equal to 1, and every non-zero element in S, there exists T in S such that ST is 1 and TS is 1 too. Okay, and we call S be a field. If S is a division ring and commutative ring. Okay, remember here, if here the multiplication satisfy commutative law, we call S be a abelian group. But here, if the ring satisfy the commutative law, we call it is commutative ring, not abelian ring. Actually, abelian ring has another definition. Okay, let me show you. S, not clear. Change the color to here. S be abelian ring. Actually, we call ring only call abelian ring only call abelian. If S is a ring and every idempotent element is center element. Okay, idempotent element means for some element A square equal to A, and the center means AS equal to SA for every S in S, and here A called idempotent, A called center. Okay, and let's define another definitions. Also, we let S be a set, and this be a binary relation. On S. Okay, see, here is binary relation, not binary operation, and we call S the system, S and the binary relation. We call it is partially ordered, or we simplify call it is ordered if the relation satisfy three laws. The first is reflexive, and second is transitive. Third is anti-symmetric. Okay, let us study these three laws one by one. Reflexive means for every element is smaller than or equal to itself. And the transitive means A smaller than B and B smaller than C, then A smaller than C. And anti-symmetric, let's see. If A smaller than B and B smaller than A, then A is equal to B. This is symmetric. Anti-symmetric. And we call S be a simply ordered. If S is ordered, and for every two elements have the binary relations. A smaller than B or B smaller than A. Okay, and we call S be a semi-lattice. Sorry, I forget to change the color. If S is ordered and each two element A, B in S have a greatest lower bound. Or we call this is inf A and B. Okay, let's see. This symbol means a binary operation on S. Satisfy if C smaller than A and B, if and only if C smaller than A and C smaller than B. Okay, let me give you some examples. First, the positive integer set with the relation smaller than or equal to. This system will be ordered set. Okay, let us prove it. Because we want to prove this is ordered set, so we should prove this three laws. Okay, for the first reflexive, actually for every element in the positive integer set, this is smaller than or equal to itself. And the second transitive, if A smaller than or equal to B, B, C, actually we also have this relation. So transitive goes and anti-symmetric. If A smaller than or equal to B, B smaller than or equal to A, then in the positive integer set, there must have the result, right? For every A, B in S, every A, B, C in S. Okay, so this is ordered set. Moreover, this is simply ordered, because for every element N and M, or N smaller than or equal to M, or M smaller than or equal to N, and this is simply ordered, and this is semi-lattice, because for every element in Nm, there must have Nm, the greatest lower bound. Actually, we usually use minimum of Nm. So this is semi-lattice. Okay, for the second example, also is the positive integer set. Here, the relation becomes to divided. This is ordered set. Okay, we prove this one by one. First is symmetric, reflexive for every integer, positive integer. This can divide itself, because n equal to n, then n can divide it. And second transitive, A can divide B, and B can divide C. By the divides relation, there must have some P such that B is equal to PA and C equal to QB, and PQ is positive integer also. Then let's see, C is equal to QB, right? And B is equal to PA, so QPA. That means A can divide C. So the transitive law 2. And anti-symmetric. For every element, A can divide B, and B can divide A, then there must exist some M such that B is equal to MA and A is NB. For some MN is the positive integer. Then let's see, B is equal to MA. A is NB, so MNB. That means MN is 1. Because MN is a positive integer, so M and N is 1. That means A equal to B. If A equal to B, then the anti-symmetric is true. Okay, so Z with the relation divides is ordered set, and moreover, this is simply. Oh, sorry, here, wrong word. Simply ordered. No. Actually, for every positive integer, if we let the okay, actually there do not have we let this binary relation be the greatest common divisor. Then maybe we do not have N can divide M. Sorry. And M divide N, such as we let M is 2, N is 3. Okay, they are prime numbers. So by the relation divide, this is not simply ordered. And let's say this is a semi-lattice. That means if say for every A, B, C, if C divides A, B, is there have some C divides A and C divides B? The answer is true. This is true because the definition of the relation greatest common divisor, we always use GCD to define the greatest common divisor. If C is the common, if C can divide the common divisor of A and B, then C must can be divide A and B. So This is semi-lattice. So we get this is semi-lattice, and the first example, this is semi-lattice and simply ordered. Let's see the third example. Okay. Also, here we use this notification to define all the subset of positive integer set, and the relation we use the include. Then this is ordered set. Okay, for the first, we should prove this is reflexive. Actually, for every set in the positive integer set, A is a subset of A. Second, transitive. For every A, B, C in the collection, and A is a subset of B, B is a subset of C, then we can get A is a subset of C. So the transitive goes well. The last one, anti-symmetric. For every set A, B in the collection, A is a subset of B, B is a subset of A, then we can easily get A is equal to B. Also, in many proving, if we want to prove the set A equal to B, we use two ways. First, we prove A is a subset of B, and second, we prove B is a subset of A. Then, these two sets is equal. So, the collection with under the relation is ordered. Is this simply ordered? Actually, this is not simply ordered because not every two sets have the relation, such as we let A be the set of 1, B be the set of 2, then A is not a subset of B, and B is not a subset of A. So the collection is not simply ordered. And is this lattice, semi-lattice, that is for every two set, is there have some lower bound? Okay, first of all, let us define this binary relation by the, actually this is intersection, right? Means A intersect B. This means let's see, if C is a subset of A intersect B, can we get C is a subset of A and C is a subset of B? And the inverse, can we get? Yes, we can get this. Okay, so by this relation, we can get the collection actually is a semi-lattice. Okay, let us see the first proposition. The class of semi-lattice can be equally defined. Equationary. Defined as the class of all semigroup satisfy the commutative law and idempotent law. That is A, B equal to B, A, and A is equal to A. Okay, let us prove this. That means the semi-lattice and the semigroup can be defined equationally. Okay, for the first, this is a semi-lattice. Then we should prove this is a semigroup. Actually, to prove this is a semigroup, it is very easy to prove, and we should prove the semigroup will satisfy these two laws. Okay, for the first law is the commutative law. Okay, actually, this is true because by this definition, say smaller than or equal to AB if and only if say smaller than or equal to A and say smaller than or equal to B. Then these two laws, commutative law and idempotent law, is true. And the inverse, we said this is a semigroup. S is a semigroup with these two laws, and we want to prove this is semi-lattice. That is, we should prove for the first, S is ordered. We need to show S is ordered, and let's see the semi-lattice definition here. Ordered, and for each two element have greatest lower bound. Has I_inf A, B. Okay, to show this is ordered, that is, we should prove this is satisfy reflexive and transitive and anti-symmetric. For the first reflexive, we need to show A smaller than or equal to A. That is, for every element in S, this is true because A is equal to A and A. And by the definition, here, A smaller than A. Okay, and the transitive, we need to show, we let, for every A, B, C in S, we let A smaller than B, B smaller than C. We need to show A smaller than C. Actually, we need to show A equal to A and C, right? Also by these definitions. Okay, how to show this one? Because A is smaller than B, so we have A is equal to A and B. And here, because B is smaller than C, so B is equal to B and C. So from here, we change the B to BC. A, B, B goes to BC. And because this is operation satisfy the associative law because this is a semi-group. So we can rewrite this by this one. And this is A and B is A, right? So this is A and C. So A is equal to A and C. Then we done. This is order, and we remain to show the infinity. Okay. Actually, the infinity is obvious. Oh, sorry. We need to show the anti-symmetric. That is, for every element A, B in S, A smaller than or equal to B, B smaller than or equal to A, we need to show A is B. Actually, from here, we can get A is equal to A and B. From here, B is equal to A and B. So A and B equal. So A equal to B. So we done. Then S is ordered and the inf is clear. So we get S is semi-lattice. Then we prove these propositions. And let us define some another definitions. Okay, see this semi-lattice. So here must have lattice, such as just like semi-group and group. Okay, let us define this. Also, S is a set, and this is a binary relation on S, and here is binary operations on S. Then we call this system to be a lattice. If any two elements A and B have infinity and a least upper bound, or we call it is spring A and B. Okay, actually this is S under the binary operation. To operation is semi-lattice. Okay, by this definition we can see a relation of simply ordered and lattice. Actually, simply ordered always lattice, and moreover, on the lattice, for every element in S, this is smaller than 0 and bigger than 0 and smaller than 1. Okay, we call an element A in the lattice is complement if A prime is 0, A prime is 1. And we call S to be complemented if first S is lattice and second for every element in S, this is a complement. And we call S is distributive. If this is satisfy the distributive law. That is A, B, C, B or C equal to A and B or A and C. Okay, in this distributive lattice, if there exists a complement, then this complement is unique. Okay, let us prove this. Suppose A prime and A2 prime is complement of A. Then we have A prime is equal to A prime or sorry, and 1. And this 1 can be written by here, a prime, and here we a or a prime. Here prime change to a2 prime, because a2 prime is a complement of a. And by the distributive law, a prime and a, or a prime and a2 prime. Okay, let's see. By here, this is 0, a prime and a2 prime, because here we can get a prime, a prime and a2 prime, and we can use this or 0, and this 0 we can rewrite by here, a prime and a2 prime, or this 0 can be written as a and a2 prime. And by the distributive law, a prime or a and a2 prime. Okay, here is 1 and a2 prime, so this is a2 prime, so a2 prime is a prime. Then this is the complement. If it exists, then the complement is unique. Okay, so let us study some example, and we finish today's seminar. I'm tired. Okay, let's see the first 3 examples. We can easily see the first example is distributive lattice, and the second also the distribute lattice, and third one distribute lattice. Okay, distributive actually in the third one, this is complement also. Okay, you can prove this by yourself, and I will give you another 3 examples. Examples 4. Let S be the set. All the S is a positive integer, and square S not positive integer. Then S and the divides is complemented distributive. That is. Okay, to prove this, we prove 3 parts. For the first, S is lattice. This is true by let this one be the GCD, and this one be the LCM. Actually, this is less latest common multiply. We simplify this by LCM. Then S can be a lattice. And the second one, S is a complement. So let's see for every element, is there exist S prime such that S and S prime is 0 and S or S prime is 1. Actually, this is true, right? Because we must have some positive integer S prime such that the GCD, greatest common divisor of S and S prime, is 0, and the latest common multiply is 1. We always found this. And the third one, we should prove S is distributive. That is the distributive law is true. Okay, let's see. For every element A, B, C, A and B or C, this is okay. G, C, D, A and B or C. G, C, D, A, L, C, M, B, C. We rewrite by this form. Actually, this is can be rewrite LCM GCD AB GCD AC. That is GCD AB or GCD AC, and this is A and B or A and C. So the distributive law comes true. By this 3 steps, we can get S is a complemented distributive lattice. And the following example is let S be the subset of the collection. Okay, how about use this form? S is a subset of positive integer set, and S is finite, and there exists some S prime is finite. This is a complement of S such that S prime also is in the collection. Then the collection under inclusion is complemented distributive lattice. Okay, also we prove this by 3 steps. First, this is a lattice. It is easy, can be by from example 1. And we let this be the intersection or be the union. Second, we prove this is a complement. This is true because, you see, by the definition. And the third one, we prove this is distributive. Sorry. Okay. Actually, this is Morgan law, right? For every element in the collection, A intersect B union C equal to A intersect B union A intersect C. Okay. Then the collection A is completely distributive lattice. And the sixth example is S. How about written by this? Collection. Also, this is a collection. And S is a subset of positive integer set, and S is finite. Oh, sorry. And here, S prime, also in the collection, is a complement of S, and this is finite. Then the collection under inclusion is complemented distributive. That is. Okay, this proof is same as example 5. Okay, so we complete today's seminar. Today's seminar we introduce some rings, definitions, and lattice ordered set, and give you some examples. Okay, thank you for your listening. Bye.